we are going to speak about multiple sequence alignment. So I'm going to share the screen. So pairwise alignment is employed when we have only two sequences or two organisms to compare. But in reality, several times we are interested to identify common genomic sequences between different organisms. This is the previous 3A domains, and it would be nice to have a multiple sequence alignment of these 3 domains. Now I'm going to present the alignment of the 3 sequences in a 3-row matrix. And we wish to get a scoring function of all 3 sequences that scores conserve alignment higher. In this case, we have to remember or to claim that while a pairwise alignment was a 2D alignment, a multiple sequence alignment will be a 3-dimensional alignment where we have 3 sequences. This first line represents the number of symbols up to a given position. I wish to give a bit more about it. The gap is not considered a symbol. So on the first column, I have A. On the second column, I have a gap. So I still have 1 symbol. In the next column, I have T. That is another symbol. So I'm going to add 1, 2. G and C, 3 and 4. Now I came back to the second line of the same alignment. Column number 0, I do not have any symbol. Column number 1, I have A. Column number 2, I have A. Column number 3, I have T. And because I have a gap here, I'm not going to increase the count. 3. In column number 4, I have C. This counting is the counting of the original strings. I'm going forward. Column number 0, 0. Column number 0, gap. So I'm not going to increase of 1. And all the other columns contain letters, because it was A, T, G, C, A, T, G, C. Now I'm going to represent in a 3-dimensional cube this alignment. Each column corresponds to an X, Y, Z. The first column is the X, the second column, the blue one, or row, my apologies. The first row is red, the second row is blue and corresponds to a Y, and the last row corresponds to a Z. So the first row is represented by the first column by 0, 0, 0, the second column by 1, 1, 0, the third one by 1, 2, 1, the fourth one by 2, 3, 2, the next one by 3, 3, 3, and the last one by 4, 4, 4. While a 2D alignment is represented as a square, a 3D alignment is represented as a cube. And while a 2D alignment has only 3 or 4 possibilities, in fact, if you consider the match and the mismatch, 2 different possibilities. A 4D alignment has much more possibilities. A cube has 1, 2, 3, 8 different points where its lines meet. One point is a final one. As a consequence, I will have 1, 2, 3, 4, 5, 6, 7 different points that allow us to identify the possibilities using a dynamic programming approach. So at each point, I have to analyze the 7 previous ones. I have 7 previous points, and the delta is the distance matrix. It is a scoring matrix. And I have x, y, z. The score is in function of x, y, and z. And we returned before, this is x, this is y, and this is z. In this case, x equal t, y equal t, and z equal t. So it will have a very good score. I cannot find the very bad score here, but I can find the bad score. Column 3 is G, gap, and G. So, for 3 sequences of length n, the runtime is proportional to 7n power 3. Why 7? Because at each point I have to look backward to 7 other points. For a k-way alignment, we are going to check backwards to all possibilities, and we must build a k-dimensional Manhattan graph with n power k nodes. Several nodes will have 2k minus 1 incoming edge. As a consequence, the runtime will be O, big O, of 2k, 2 power k, n power k. So it's going to be exponential in function of the number of string to align. Now we wish to reduce the computational complexity of this problem, and we are going to check that in reality every multiple alignment is computed or can be computed using pair wave alignment, like I'm going to show here. I'm going to align the first one to the second one, the first one to the third one, and the second one to the third one. So we start setting arbitrary pairwise alignment. and we wish to get a multiple sequence alignment. Now I'm going to show you a profile representation of a multiple sequence alignment. Here I have 5 symbols, the 4, A, C, G, T, and the gap. And I'm going to represent in the column the percentage of symbols that are used in the column. In this case, I have 1 gap, 3 C and 1 T. It means that C will be 60%, T 20%, and the gap 20%, and going forward. In this one, I have only 1 C and further gaps. C is 20% and the gap is 80%. The point is that a greedy approach is to choose the most similar sequences and combine them into a profile, thereby reducing alignment of K sequences to an alignment of K minus 2 sequences and 1 profile. And we are going to iterate. This is an example. I have 1, 2, 3, 4 sequences. So I'm going to do 6 pairwise alignment. That are the first one, the second one, the third one, and I'm going to report the score of the alignment. 2, 1, 1, 0, minus 1, minus 1. The highest score is 2, so S2 and S4 are closest than any other one. And so I can create a profile called S24 that is composed by the identical nucleotides and the not identical one reported as an option. In this case, the consensus is GTC, T or A, G, A or C, A. And now I'm going to align against 3 sequences, S1, S3, and the sequence common to S2 and S4. And this presentation is concluded. Okay.